Yes,
So
thank you.
please, the floor is yours. Thanks.
Thank you, Andrea and Julian. I feel a certain amount of pressure being the first person, but maybe I can set a low bar so people feel welcome to surpass me on future talks. So that's how I'll deal with the pressure. So I'm going to do something maybe a bit heretical and take this NEMO ocean working group and mostly spend time looking at the atmosphere. So please forgive me for that, but that's where I have most of my expertise, at least now. But I think there'll be some interesting things that we can consider bringing down into the oceans. And I'll thank my my collaborators, and also Maelstrom, which you see down here, is an interesting project. If you've not come across it, that's what pays for me. It's sort of we're trying to create some interesting benchmark problems or data sets around the sort of weather forecasting workflow, and then try and make some progress on them. So let's see. Yeah. So in atmospheric modeling for weather or climate, we have lots of processes that we would ideally like to capture. That most of them happen on a grid smaller than we can afford to run. And so we develop in one way or another sort of subgrid closure schemes, subgrid parameterization schemes, to get the impact of these many and interesting processes, many and varied processes back on our represented grid scale. And yeah, there's lots of interesting and complicated physics here. And so the question is sort of how might machine learning be useful in this sort of world of processes that we don't have perfect models for. And I broadly see there as being sort of three pillars of approaches one can take, although I think you can actually start to blur some of these lines together and see sort of intersection between those as how machine learning would be useful. So the first column is going to be sort of trying to emulate or recreate an existing model component. This is something that you'd be used in your sort of operational weather or climate model. And really here, there's very clear sort of what you're trying to do. You're trying to reduce the computational cost. And you're maybe thinking this is possible by two means. One, it's going to somehow find through some clever machine learning architecture, some sort of shortcuts, some bits of the physics to sort of cut out, approximate, or hide beneath. And the second aspect of that is you might think that just even if you've got the same algorithmic complexity, it's easier to port a machine learning algorithm to GPUs than it maybe is some of our conventional code. Although obviously not impossible, and there's quite a lot of active work in many places looking to do this. And so there are some examples of these. In fact, the first example that I know of is back in 1990. So this is not a new idea, but it didn't really take off then. And then there've been some more. I'm going to do whatever when you try and capture what everyone's contributed to a field. I'm going to forget some people or miss some people. So if you see someone, please tell me so that I can include them next time. And please let me apologize to them or you if it's you. And so I think this has been particularly popular in the field of radiative transfer, radiative heating, but it's also been tried for some other aspects of that sort of block diagram of applications. So then you can try and emulate an increased complexity model component. So this might be something that you can't currently afford to run in your operational scheme, but you think it's a better representation than something you've already got. So this might be radiation, where actually we have a whole hierarchy of different approximations to the equations, and we can think of taking fewer, sort of putting away some of those approximations, generating some data sets and training on that to shortcut this increased complexity component. And I guess this has been seen in radiation and I think cloud microphysics. And then the third and definitely the most bold, and the one that I'm gonna capture here, and then is not something that I've spent much of my time on, is this idea of learning a new parameterization scheme. So this is where you would use data from high resolution simulations or observations, and you've got lots of interesting and exciting challenges to get a stable parameterization learned into your model. And there's loads of really exciting papers, and Julian was sharing a paper just this morning doing something in this ilk. And this has been more popular in the atmosphere for convection parameterization, and is also, I think, where I've seen the most work on the sort of ocean or on the turbulence perspective. But we're going to focus on these two, where I think you can definitely blur the line of what is an existing model component or what and the sort of moving over to this increased complexity component. But all of them have a similar sort of workflow of, for these first two columns at least, of running your existing Earth system model, coupled to this either affordable or currently unaffordable component. Hopefully it's not so unaffordable that you can't afford to run it all together, or else this approach doesn't work. And then generating your data sets to train machine learning to just reproduce this input to output mapping. So it's a regression problem. You maybe don't even have any arguments for incorporating uncertainty into it because you have a deterministic model that you're looking to recreate. And then the tricky bit comes in trying to connect the machine learning model back into the Earth system model. And then you want to run simulations to understand the coupled impact of your emulator on your forecasts, because typically what you're not doing is actually training your loss function isn't the actual thing you care about. You train about some sort of offline mean squared error, mean absolute error, but you care about your impact on the forecasts of weather or climate. So our sort of first contributions to this venue were, first of all, in the process of non-orographic gravity wave drag, which is a good tongue twister to keep me on my toes. And this is sort of trying to capture the unresolved impact of things like sort of convectional fronts that generate gravity waves that propagate upwards into the stratosphere and then break, depositing momentum further up. And here we're doing a bit of column 1 and a bit of column 2 actually, where we're trying to generate data from an existing scheme or a more complicated version of this. And here we kept the machine learning really, really simple. So we're just looking at a fully connected neural network, a dense neural network, a multi-layer perceptron, whatever you like to call that kind of flavor. And what we see here is, if we think only about an offline error, that was very much a tunable parameter. So this is the complexity of my machine learning solution. This is my offline error, so not coupling, just trying to represent a process that I pulled out of the model. And I see I can sort of drive that to some extent into the ground and make that more and more accurate, but that doesn't necessarily tell me what's going to be a good model coupled to the system. So I actually need to generate a whole set of these models and see which of them are good enough so that I can't even see their error in online forecasts. And we do this for non-orographic gravity wave drag, then putting it back into ECMWF's IFS model, and we see really quite nice results. So this is a process. One of the interesting reasons, the reason we sort of decided to explore this process is we're learning to our mapping function from a regression problem is learning from an instantaneous field to calculate the instantaneous tendencies, but the process is most obviously visible on a sort of order year timescale, because we're trying to capture the impact of things like the QBO, where we have this descent phase. So this is a visualization of equatorial zonal winds over time measured in years here, where we can see this weakening and coming down through the atmosphere of this feature. And so this is something that you're going to train on increments of sort of order hours, and you need a model that can recreate this process. And we see that our emulators do this quite nicely, and they also don't degrade our forecast skill. They actually improve our forecast skill slightly, because we take some elements from column 2, we make a more complicated version of our model, and we're able to recapture that, albeit most of the actual improvements are very high in our model and only over the poles. So currently this is not something where we're pushing towards operations, because it's not providing a big enough boost to our performance. But the key element, or one of the key elements we learned from this, was this plot here in terms of the offline error really wasn't, I mean, it was correlated with how well we did online, but there was no clear sign, or there became a point beyond which, a sort of point of no return, where bringing in more floating point operations, more complexity into our machine learning solutions, while it drove down the mean squared error, there was no discernible impact on the forecast quality or the ability to capture these long-term effects. So yeah. But this was a great test bed to sort of learn some concepts, to build some workflows. And then more recently, we've been looking to do the same thing, but with a much more impactful component. And that is with the radiative transfer component of our IFS model. And we've been trying to learn to replace, so we're in the the left-hand column of my sort of pillar, trying to replace the scheme that will be shortly operational in the IFS scheme. And this has loads of interesting physics all mixed together because we're interested in how gases, aerosols, and clouds all impact the heating of and cooling of the surface, and also the heating and cooling of the atmosphere. But there's also elements, we have a project going on at the same time to do this middle column aspect as well, but I'm not going to talk about that in so much detail. And so another thing that I wanted to hit on a little bit was, I think if you look at this sort of wider field of parameterization emulation, some of the things we're getting better at are keeping humans in the loop more and putting more of our existing knowledge into the system. And this is something we've tried to take on with this project here. Of not just using a sort of multi-layer perceptron, of using a fully connected neural network, because these don't necessarily learn very well, but they might make us nervous about spurious correlations. And if you think about what I'm trying to do here, so I'm trying to take in many different atmospheric columns or atmospheric fields on columns. So I'd have vertical profiles of, say, temperature, humidity, cloud fraction, and plus some surface descriptors of, say, surface albedo. And I'm trying to predict some fluxes or some heating rates on the vertical column out. And in a fully connected neural network, these are all getting mixed together, and there's no sort of consistency in the same physical processes, same physical dependencies are being encoded at the top and bottom of the atmosphere or anywhere in between. So someone that I've collaborated with, Peter Ukkonen, has proposed a very nice model to try and mimic both the physics we'd like to capture and also the sort of data flow of the existing solver. And that's by trying to use recurrent neural networks. So I'm going to talk a little bit about how the shortwave heating process works. So here we have incoming solar radiation, which is propagating through the atmosphere, and it's either being absorbed or it's being reflected. And so what we would like to, so we have a very directional process, but it's not just one direction. So we might like to first think of that as a single RNN propagating through. So in RNN, you have this sort of level-wise forcing. RNNs are recurrent neural networks. These are often used in the time dimension to sort of move time series forward, given some external forcing. But here we're going to think about them in space, and we're going to think of them going up and down our vertical columns, and we're doing this in parallel across the entire atmosphere. And we think about, we have our incoming solar radiation is our starting state, and then we're going to have our forcing being our level dependent atmospheric field. So this is telling us the humidity, the pressure, the cloud fraction at that particular level, and then this is propagating down the atmosphere into the surface. We then have a small neural network to calculate how this flux interacts with the surface, and then send another recurrent neural network upwards to try and capture this sort of first order reflectance back up the column. And we're passing these states through one another so that this information still has a way of propagating. And then we include one final recurrent neural network to capture a remaining sort of reflectance that's in the existing solver. And this gives us some fluxes. And so what this does is it builds in the same sort of directionality that the variables at the 137th, so that's the bottom of our atmosphere, cannot sort of directly impact or very easily impact the fluxes out at the top of the atmosphere, except through this relatively complicated path. So we remove the ability for the model to find spurious correlations and use them to build an unphysical model. That works for shortwave. For long wave, you need to think slightly differently because the directionality of the process changes, but we have a similar idea. So the second element is about actually trying to encode some of the physical equations in the model. And for radiative transfer, you have we have a duality between the fluxes of the sort of natural output of our model. So that's how much watts per square meter is going from one level to the level above it or below it, depending on the directionality. But the thing we mostly care about in the atmosphere is the heating rate. And that's the sort of the vertical gradient of the flux. So that looks at the difference between two neighboring fluxes, and then divides that by the gradient of pressure, which is a sort of our vertical coordinates here. And when I tell you that the pressure differences at the bottom of the atmosphere are order 100 hectopascal, and the pressure differences at the top of the atmosphere are order 1 times 10⁻², you might see that we have some very strong sensitivity that could be in this problem. So if we have a small error at the top of the atmosphere, that could get heavily sort of inflated and give you very large inaccuracies in the heating rates at the top of the atmosphere. And so what we do is we encode this equation into our neural network and make sure that it's accurately satisfying both the fluxes and the heating rates, so it's able to cope with this sensitivity. So what does this look like? So this is for shortwave. I'm showing you some columns. So these are 4 randomly chosen columns from some offline data set that I generated. And the top of the atmosphere is on the left, the bottom of the atmosphere is on the right. And we have the shortwave downward fluxes. So this is what's coming in from the sun and then what makes it all the way down to the ground. And then the shortwave upward fluxes. So this is how much is being reflected backwards. And then this is the heating rate, which is sort of the vertical derivative of the difference between these. And you can first see that this is a relatively complicated process. There's some very sharp gradients we would like our model to capture, but also there are 2 lines in each of those. And if you can spot the difference between those 2 lines, then you have better eyesight than I do. Well, that's not quite true. This profile here has a place where the 2 lines are slightly off, but we've done a very good job through incorporating as much physics as we can in learning this. And we do a similar job for our long wave, but I'm, in the interest of time, going to blast past that, because what I talked about before is that offline looking nice wasn't necessarily a predictor of how we do online. So we're sort of training for a sort of fake loss that isn't our primary objective. Our primary objective is good forecasts, accurate 2-meter temperature forecasts or Z500 forecasts. So the first question is, how do we do online? Not how do we do online, as in, what is the methodology for getting our machine learning models into it? And I don't know if we have representatives today, but I know part of this working group has representatives from SmartSim, which is a really nice system for getting machine learning models into Fortran code. We're currently using quite a simple approach, which has its drawbacks, but it means it's quite easy to get a model into Fortran. It's maybe less easy to make that run really, really quickly, but for testing scientific impact, it's really nice. So this is really just providing a Fortran interface to a few of the different backends people like to use for inference. So this could be TensorFlow, could be Onyx or TensorRT, which is an NVIDIA product. And what this looks like in your Fortran is initializing a model and then just calling infer on that model to get the answer. And this is a public repository for a project we've created. So if you want to test getting a model into your Fortran workflow, I really recommend this as a quick way to get that started. So what does it look like? So we run lots of simulations and then try and investigate the impact. So this is from a suite of 90 experiments over the summer from 2020. 2021, sorry, which was never shown to our model. We never saw data from 2021. And we're looking at 30 kilometers, which is coarse, but something useful for doing quick exploration of our model, or relatively coarse for our operational model. And what we're seeing here, this is the change in root mean squared error for temperature forecasts compared to the no machine learning model, so the existing version of the model. So with this sort of emulator approach, we cannot aim for blue. I mean, we get some spurious sort of fluke blue from not running enough simulations, but what we're aiming here really for is white, which is certainly no improvement. That should be impossible, but no degradation. And broadly speaking, we do a really good job of this. So we don't have no red, but we have red only above 100 hectopascals, so quite high in the atmosphere, and only above the sort of northern hemisphere pole. So room for improvement, but stable models over quite long simulations. And when we look at things like 2-meter temperature or skin temperature, which we're going to come to, except we're running out of time, then we don't see any impact. And we'll keep blasting through because I think I have about a minute left. So speed is obviously the main purpose that we would do this, and I don't have a good answer for people yet on this. So on CPUs, we are slightly faster than our existing counterpart on CPUs, but probably not enough to motivate putting machine learning into the loop. What we're working on at the moment is some of the technical complexity to couple GPUs into our into our workflow, into the IFS. And I'd love to give you a short update when we have that on how much faster it is. We can do some decoupled tests, and those tell us that the emulator will be much, much faster, but that's not a very fair test because you have to be very cautious about the data transfer costs of moving the inputs to the radiation scheme onto the GPUs, wherever they are on your cluster, and then bringing them back on. So hopefully in the next sort of month, I'll have some robust results on this. So yeah, so that's the sort of summary. We can do a nice job of emulating these processes to a sort of very high degree of accuracy. The computational advantages are still ongoing, but importing as much physical knowledge as possible certainly helps. So what I didn't tell you is about all the failures when I use things like multi-layer perceptrons or don't include lots of these physical ideas in, my models don't converge to as good a solution. So these are really helpful. They don't just make us feel proud of ourselves for coming up with clever ideas. And with that, I think I will stop and take some questions. Thank you.
Thank you very much, Matthew. Very interesting, especially the relationship between the machine learning model and the forecast accuracy. So any question, you can please raise the hand. I'm not sure, sorry, I'm not sure if they come order to me, but I see Julian appears as the first. So please, Julian.
Yes. Hi everyone. So thank Matthew. It was really nice, and I really enjoyed all the work. I have a question at the beginning of your talk, but maybe you can reflect on the whole work you've done. You kind of merge the objective of having learning new parameterization scheme using high resolution simulation or using observations. But would you say this is the same objective? Because the point I see is that with high resolution simulation, you can have the control over the source of bias in your model, so you can control which parameterization you are learning. While if you do that with observation, depending on what you observed, of course, you have a total bias, and how you see the venue to learn parameterization scheme from observations.
Yeah, I think maybe it was a bit of a lazy approach to not create even more columns in my diagram. I agree that they don't have exactly the same challenges, and probably if someone was trying, if I wanted to choose one of those routes for myself, I would probably start with high resolution simulations, because I think the hurdles to overcome are less challenging. I think getting thorough enough data from observations to design a proper to train something seems very, very challenging. I guess I was just floating it up as an additional way that we're still trying to incorporate this, achieve the same goal of making a better parameterization scheme. But you're right, they're not exactly the same. They will have different challenges.
Okay, and if I may, I just have a very detailed question, very quick. I think it was on the slide, but I'm not sure. On Infero, you can couple with Fortran, but is it also okay with C++ and C?
Yes. Well, with C you can get to TensorFlow quite nicely anyway, because TensorFlow already has a sort of C. It has all the C bindings anyway. So I think if you're going to do that, you might not even want Infero. I think we have C++ as well, but I don't make me promise that. But I think we've done some work in C++ as well. Yeah.
Thanks.
Marcin, I see you are the first on the list.
Well, Matthew, very, very nice talk. So I have a question regarding Infero and the performance. So I imagine there must be some data movement to move things from Fortran to whatever the backend is used by Infero, right? Is it something visible in the profile Does it affect performance? Or?
Yes, we have a data copying or data movement aspect. Yeah, there's a when you shut down a model in Infero, or when your simulation or when your Fortran code closes, it will automatically shut down the model. It gives you a few lines on where time was spent in terms of the actual inference time versus the other aspects. So there's a little bit of that. I think there's room to expand that, actually. I think now, as we're sort of exploring the coupling with GPUs, we're probably going to realize that we can add more things to this, because there'll be more in-depth heuristics, but there's or more in-depth sort of utility that we can add there. But there's already some information on the moving of data and the actual raw inference time.
Mm-hmm. And out of curiosity, because you mentioned that the neural network model runs only marginally faster on a CPU compared to the physics-based code. So I imagine it's more efficient computationally, because you probably do these matrix vector multiplications in the neural network. So it must be that it just does more floating point operations, right? To solution.
Yes, I think there's possibly an element of that. I haven't dug down into that. We could probably get a approximate count of how much floating point operation. We know how many floating point operations are going to be in our neural network scheme. We could probably come up perhaps with a good guide for radiation. We were able to do this with gravity wave drag, and know the approximate computational cost of gravity wave drag to compare those two. But I think your intuition is probably right.
Okay, thank you.
Thanks, Julien. Please.
Yeah. So thanks a lot for this talk, and I disagree. This sets the bar quite high for the upcoming talks, Matthew.
Thank you.
Yeah. I was wondering whether so here you're trying to make so for this first undertaking of trying to emulate an existing code component, you're trying to first emulate it as precisely as you can, and then you plug it back and see what it does in practice. And you don't want to degrade the performance of your scientific performance of your pre-existing code. So the point is, there's obviously a trade-off here between precision and complexity, and probably therefore the cost of inference itself. Have you started like making this rationale? This rationale for choosing the precision of so basically, how good should be your emulator is something that you can adjust depending on the cost you want to get in the end. So have you started like playing that sort of game?
We played that game in the non-holographic gravity wave drag case, but there was a much simpler target there. No, I think that's is one of the next avenues to explore, really. My broad overview in the project was to try and drive the error into the ground to find sort of like how good I could make it with my data set, and check that was good enough for stable simulations, which it is. I still think there's room. I want to see if I can get even closer. But then, yeah, one of the next steps is going to be to pull that back a bit and see how that impacts it, because I don't really have a good I've not done the exploration to sort of make it twice as cheap in terms of, say, the degrees of freedom or the floating point operations, and see whether I can even spot that in my forecast. But that will be an important component, and then a discussion to be made with if one even thinks about going operational, like what is an acceptable error versus how much I can give you, because you'll have that two-dimensional space to deal with.
Okay, I don't know if there are other people. I have a question myself. Very shortly, I remember from some old presentation, perhaps, that at NWF you spend, computationally speaking, much more time in NWP on the 4D VAR and not on the forecast step, right? So, which obviously opened the question if you've been thinking a way to linearize the code using the automatic differentiation in the machine learning libraries, or any other idea, and probably this will change a bit the scenario of speed and accuracy, I guess. So if you have,
I had a slide on this. I had a slide on this and then I closed my slides thinking I've dealt with all the questions. So I'm not going to try and bring them back. We've done this already for gravity wave drag, where we've used our emulator to generate the tangent linear and the adjoint components necessary for our 4D VAR algorithm. And we didn't see any impact on the forecast quality when we used machine learning to generate these components. So the initial condition was just as accurate to at least the testing that we did. However, non-orographic gravity wave drag is a light touch component in the model, and so I mean, if you take away the components, you can see a degradation, but it's a very small element. So we now and the models we had were very simple, so differentiating them even by hand was very easy. If you have a multi-layer perceptron, writing down the derivative of that or even the adjoint of that is very simple. This is another direction that we're heading. So we have the version of radiation that we used in our code for tangent linear and adjoint is old. It's compared to the version that we use for the nonlinear model, because keeping it is a tough task. So there's room here to actually improve the forecast quality by having a closer parallel between the tangent linear model and the nonlinear model. How we go about this, whether we can, how much of TensorFlow's or PyTorch's sort of automatic differentiation we can leverage, is still something that I haven't got an answer to. I think we can pull in some of that, but whether it has already exposed all the functionality that we would like, or whether we'll have to bring some in, is still to be done. But I think it's a really exciting component. And your question that wasn't a question at the beginning, I believe at the moment it's about an hour for the data assimilation and 1 hour for the forecast. So they are comparable, but obviously those are both tuned, right? You could change the complexity in one or the other component and change that balance.
Okay, thank you very much. We have another question from Redouan, please.
Yeah, thanks, Andrea. Hi, everyone. Thanks, Matthew, for the nice talk. I'm just curious, actually, about the part where you incorporated the equation. Was it done, I mean, in the loss function, or was it like written directly in the architecture? Just curious to know.
You could have done it in either, because actually all our model cares about the end when we plug it in is the fluxes, and then the heating rate is derived elsewhere in the model. I chose to bring it into the model, to our neural network itself, as a custom TensorFlow layer, which is very easy. You can do the same thing in PyTorch, but they're very easy to write. You could have written it down as a custom loss function, and you get through, I think, a very similar perspective. They're doing the same thing, right? They're still providing you with the same gradient information. It was just nice to have a model that was kicking out heating rates ready for me. But yeah, I chose to do a heating rate layer.
Great, thanks.
Okay, I see Vasilios, please.
Hello, everyone. Hello, Mathieu. Very nice presentation. I have just one question is, at some point in your presentation, you said that you train your model with a deterministic model. I was wondering if you expect to increase the machine learning method by using ensembles, or results would be constrained by choices in the perturbation scheme. I don't know, any comment about this?
Sorry, I missed a word. Can you try again with the beginning of that explanation?
Okay, well, my question was if ensembles can be used to train a model instead of a deterministic model.
To my mind, that's probably more what you want to be doing, and an interesting thing to be doing in that third column, where you're trying to learn a new scheme. I'm not sure it's as clear to me the rationale for doing it when we're trying to just recreate an existing deterministic function, unless we were having a very hard time doing it. But as you can hopefully see, I do a really nice job of creating it. So I don't think there's a place for that here, but that's not in parameterization. In parameterization learning more broadly, I definitely think there is room to do that, because there you would be looking to learn an underdetermined problem, perhaps depending on how you generated your data set, and there you probably want to be able to sample from that. But given that we are actually doing a deterministic element, I don't think it's as clear that our ensembles are useful.
Okay, thanks. Other question now or never? I see no other hands raised. So thanks again, Matthew, for the very nice and interesting talk, and again for being the first one on the spotlight. So